And first up, we have Dr. Brannan from Manchester, the University of Manchester. He's going to talk about a new class of OLED emitters. And I know I want to listen not to me at this stage. So, Dr. Brannan, you have the stage. Thank you.
Thank you. Thank you, Ron. Hello, everyone. It's my pleasure to be able to present this to you today. Yeah, I'm Alexander Brannan from University of Manchester, and I'm going to be discussing CMA emitters and their use in OLEDs. So I'm going to be first discuss background on emitters and OLEDs, and then explain what CMA materials are and why they're great for OLEDs, and then give some application cases. So first off, so this is a slide that might be familiar to a lot of people, but I will go over it again briefly. So upon charge recombination or excitation in an electroluminescent device such as an OLED, your excitons or excited states will be made in a 25% singlet or 75% triplet population. So we have three main families of emitters in OLEDs. First, you have fluorescence that emits only through the singlet excited states. So therefore, theoretical maximum EQE or efficiency is only 25%. That's the problem with them. However, they have fast radiative rates, so that is the benefit. Phosphorescent emitters, which are currently used in OLEDs, they have a maximum EQE of 100%. This is because they can harvest both the singlet and the triplet excitons as they emit through the triplet excited state. However, the issue is the slow radiative rates, and that's more critical for the blue emitters. And then we have the new family, which is TADF, and where you get an up conversion from the triplet to the singlet excited state, and then you emit from the singlet. So because you can, again, harvest all the available excitons, the maximum EQ is 100%. And the good news is they show faster radiative rates than the phosphorescent emitters. So what is TADF? That's thermally activated delay fluorescence. And it's called thermally activated because this in-system crossing, or ISC, is thanks to the thermal energy which allows the up conversion. So what makes this in-system crossing, what determines the rate of the in-system crossing? There's two fundamental parameters that we can change. So the first is the energy difference between the singlet and the triplet. And the shorter or the smaller the energy gap, the faster this reverse in-system crossing will occur. The way you can minimize this energy gap is to minimize the HOMO-LUMO overlap. And this is why you have donor acceptor systems commonly used for organic TADF emitters, such as 4CZ-IPN. You can see the donor is that carbazole highlighted in purple, and the acceptor is the phenyl ring in the middle. So because the HOMO-LUMO has minimal overlap, there's a short gap, and this allows for TADF to occur. But there's also another parameter, and that is the spin-orbit coupling, the SO. Spin-orbit coupling is a constant that is related to the mass of an element. So the heavier the atom, the higher the spin-orbit coupling, and the higher the spin-orbit coupling, the more fast or the more allowed the in-system crossing is. And it's very important to have fast in-system crossing because this will allow higher quantum yields and faster radiative rates. So if you have a purely organic TADF emitter, you will not benefit from this contribution of spin-orbit coupling. But if you're to add a heavy atom, such as a metal, well, now we can hope to get lifetimes less than 1 microsecond, and that's where CMAs come in. So what are CMAs? CMA is carbene-metal-amide. So the amide is an anionic donor ligand, and that is where the HOMO resides in the molecule. And the carbene is a neutral acceptor ligand, and this is where the LUMO is. If you're not familiar with the terms HOMO and LUMO, you can think about it as where the charge is localized in the ground state is the HOMO, and where the charge is localized in the excited state is the LUMO. It might be an oversimplification, but for the purpose of this presentation, it's okay. And then these two ligands have a single metal atom that bind them together, and those metals can be copper, silver, or gold. And I like to think of this metal atom as a single atom metal wire. This is because the metal facilitates the charge transfer between the donor amide to the acceptor carbene ligand. And because we have metals, now we can get contribution from the spin-orbit coupling. And what does this lead to? This leads to fantastic photophysical properties.